All right, good morning, everybody. So my job is to make you not regret getting up early after the attendee party to come to this talk. So hopefully I'll make it worth your while. So my name is Brandon, and I want to start today by telling you a story. My wife and I bought a new house about 4 years ago in Austin, Texas, where we live. And it was an older house, but it had a lot of renovations done by the previous owner, whose name is Zeke, by the way. It's a very American nickname, Zeke. He had done a lot of interesting things to the house, some good, some not so good, and some things that, well, we basically created a verb form of his name to describe the kinds of things that happened that he had done to the house that we just couldn't explain why anyone in their right mind would ever want to do. So to Zeke something in my family is to have royally fucked something up, right? The idea here is you tried something, it didn't work, terrible idea. We use the word Zeke to describe that. So for instance, a few examples from the house. If you built a basement in the house but didn't bother to water seal it so that if you ever got rain, the basement would tend to flood, yeah, you Zeke that, definitely. Or for instance, if you hired your next door neighbor to do some electrical work for you, maybe doing him a favor as he's starting his new business, but then refused to pay him, so he and his buddies broke into your house and took their retribution on your appliances. Yeah, you Zeke that, definitely. By the way, this verb actually works really well in situations ancillary to my house. Like for instance, maybe you stayed up too late the night before a talk working on your demos. Yeah, you definitely Zeke that as well. And so this is, the reason why I share this story is because one of the many Zeked up parts of our house is this washing machine that we inherited that we've now since replaced. But we have this, relatively nice LG washing machine that my wife and I inherited when we moved into the house that we thought was actually working fine once we purged out this weird Zeked up smell that we had no idea where it was coming from and sort of had to give the whole thing a big detailed clean, and it seemed to work just fine. But then it started about a year and a half ago, it started doing some very interesting things. One thing is it actually got quite loud when we would run it. Almost to the point where it sounded like things were grinding inside of the dishwasher. It's not generally a noise that you want to hear from your appliances, a grinding noise. Usually we don't grind the grime out of our dishes. The other thing that tended to happen after a while is if we ran it at certain times of night, it would actually trip the breakers in the kitchen. The GFCI breakers inside of our kitchen would trip. If we ran it only at certain times, you could run the dishwasher at 8 o'clock in the morning and it'd be fine. You could run it at nighttime and it would tend to trip. And if you were running the washer and dryer, which are in a totally different part of the house, that seemed to create some association. We never could really figure out what was going on. But my wife and I, as human beings, we were able to sort of put two and two together and realize, okay, we probably need to get this thing fixed. Well, we ended up replacing it entirely because, I don't know if this is true here, but at least in America, dishwashers are constructed in such a wonderful way that once they break, it actually costs more to fix certain things than it does to just get a new one. So that's what we ended up doing. So we were able to use our ingenuity and our life experiences to pretty much determine, all right, this dishwasher needs to be fixed. It needs to go. But what if, in this crazy situation, this dishwasher was one of a fleet of industrial dishwashers that existed on some hypothetical industrial floor somewhere with no one actually monitoring these things, and one of the dishwashers actually went bad, caught fire at 2 o'clock in the morning, and there was no one around to observe it, right? In my wife and I's case, we heard the dishwasher day in, day out. We were able to determine over time, something is wrong, something needs to be fixed. When we start talking about industrial equipment in larger settings, in larger environments, we run into a problem of how do we actually know that something is broken? And this, I think, is why we as humans tend to be really enamored with this idea of machine learning. We are not always present when things break. Sometimes things break even if we weren't able to predict it in the first place. And so we're enamored with this idea of machine learning as a way to impart our knowledge onto a computer so that it can do the observation for us, that it can put two and two together for us. And so what I want to talk about today is really two important things that'll sort of serve as the foundation for this entire talk. One is that data, the things that we talk about when we look at machine learning, You know, every machine learning problem starts with collecting a data set, or at least figuring out where you're going to get your data from. That data never actually comes from the cloud. We talk about machine learning in the context of cloud computing, but we do so because cloud computers are inexpensive and very powerful, right? But the reality is that every ML problem starts in the world, and that's an important thing that I want to start with today. And the second is that machine learning is fundamentally a human discipline. I don't know if anybody was at the .NET Rocks panel that we did last night on the ethics of AI, but fundamentally every problem that exists in machine learning today is a problem that we as humans have created and a problem that we also can solve, but it starts with how we build those models. And so there are three big ideas that I'm going to communicate over the course of the next hour. First is that machine learning is human teaching, that it starts with us. The second is that training, yes, is absolutely meant for the cloud. We will continue to rely on very powerful cloud-based computing architectures in order to do ML training for us, but that the real work in the machine learning world from now and into the foreseeable future is really in the Internet of Things, is really in the world around us. So let's go ahead and dive in. First, machine learning is human teaching. So because this is an ML talk, I have to show you some sort of Venn-like diagram that illustrates the difference between AI, deep learning, machine learning, all of those things. I'm not going to spend any time talking about AI today, other than to say that, well, AI just represents every sort of computing style problem where we're trying to impart some form of intelligence upon a machine, upon a computer, in order to do something from us. Now, machine learning is a subset of artificial intelligence. It's really designed to turn our classic algorithmic problem-solving approach on its head. So when we, as programmers, traditionally have tried to solve problems, what we do with a computer is we give it the data, we create an algorithm, and we say, now give us the answer, right? We give it a formula, some sort of code that actually represents how to form the answer based on the data that we provide. And so the real work here for us as engineers is here in specifying the algorithm and the data. And while I admit this is overly simplistic, where machine learning is different here is what we're trying to say is we have the data, we have in our sample data set the answers, and we need a machine to actually tell us what's the algorithm here. We're not quite sure what the association or the correlation between the answers and the data actually is, so tell us what's actually happening here. And so the entire process of machine learning is around structuring ways of associating data to the answers and finding tight correlations between the two. Now, deep learning takes this a step further. Through this, I'm sure many of us have seen a diagram like this before, a relatively confusing looking diagram, but effectively the point of deep learning is to find correlations among complex data by creating a mapping between input layers, hidden layers that perform a lot of back and forth propagation of weights and measures into an output layer that ultimately gives us the results. And this isn't a very useful graphic by itself, but effectively what deep learning does in many cases, especially if you're doing something like a neural network, is it works through a process of actually identifying features. What you're doing in this place is what's happening in the case of deep learning is that the algorithm or the machine is attempting to find patterns based on data that is close to one another. It's first looking at light, dark pixels, then identifying edges, combinations, features, and then combinations of features. But this feature extraction idea is really where the power of deep learning fundamentally comes. Now, one of my favorite explanations of machine learning in general and deep learning specifically comes from a book called Grokking Deep Learning by Andrew Trask. I highly recommend checking that book out. It's from Manning. If you haven't read it, it's a really easy introduction, very good code, and you actually work through the process of, in a framework-free way. There's no TensorFlow, there's no PyTorch. You're basically working through building out and understanding how deep learning works using Python from first principles. And so one of the examples that Trask uses in his book is what he refers to as the Streetlight Problem. So let's say you find yourself in a country that you've never visited before and they use, for some strange reason, non-traditional streetlights. So some combination of these three lights being on or off tells the population whether you can walk, whether you can cross the street or whether you need to wait. And so as a human, you will sit back and you'll observe, okay, these two lights on means I need to stop. These two on means I need to walk. Okay, this one means I need to stop. And as a human, it doesn't take long for you to figure out maybe 5 or 6 of these to pretty much infer that the middle light is effectively key. For some strange reason, this country has decided that the outer lights need to be there, but there's really only one that matters whether you need to walk or stop. It's the center one. Center one's on, you walk, doesn't matter what's going on with the other two. For whatever reason, they thought that was a good idea. The process of deep learning is really taking this sort of a model and creating something that a machine can understand, right? You're teaching computers to effectively find correlations between what you know and what you want to know. Given this data set, you want your computer to tell you, with a certain combination of lights, tell me when it is okay to stop or when it is safe for me to cross or whether I need to wait. And so the process of machine learning looks like this. You break the street lights down into a pattern of 1s and 0s effectively that represent on or off. You then create a program that creates this data set. In this case, this is just a couple of NumPy arrays, and then effectively just create a loop. And through your loop, you're basically going through your data set, making a prediction, and then calculating the error, and then adjusting your weights based on how large or small the error actually is. This is effectively the way that building a neural network works in the deep learning context. And you're working through this over and over and over again. The inputs to the model the first time are basically just guesses. The machine is saying, it's just picking a number between 0 and 1, seeing if it works, and then making it larger or smaller based on how far away you were from the input. And so when you run this in the console, you're basically working from random predictions and effectively and eventually coalescing on something that is actually relatively close to what we wanted to see in the first place. This is effectively the work. You're teaching your computer to find correlations between inputs and the outputs that you want, and it does so using its own approach. But one thing that I want to underscore here is that every single step along this way was a human concept, right? The only thing that the machine actually did is execute the code that I wrote for it. Just like writing a classical algorithm, there wasn't anything automated, right? I defined the data inputs. I defined the process that the machine needed to use in order to give me the outputs, and all it did was exactly what I told it to do. Right? This is still a human exercise, much like creating traditional programs, and it also means that machine learning comes with the same problems that human programs do. But as a human, I'm responsible for creating the inputs and outputs, for defining the model architecture, and for training, evaluating, and tuning the model. So that's the first thing that I really want to start with, is this concept of, as much as we talk about the value that machines add to the process, they're really just giving us their processing power and their brain power in order to help us find answers, but we define the context for that. Now let's spend a few minutes actually talking about the training process, and training being meant for the cloud. So as I start with that, I want to talk about also this idea that machine learning is not really done in any one place. Again, the discipline of machine learning, when we talk about model creation to model deployment, inferencing, all of those things can happen in different places along the process. Right? When you're doing development, when you're doing training, when you're doing inference, these are discrete parts of the machine learning workflow, and each one of these can happen in a different place on a different computer. If you are a developer and you're building your machine learning models, very likely you could be doing this in Colab, you could be doing this in Jupyter Notebooks, where you're effectively hosting the workflow or the work power on another machine. But most data scientists and ML engineers are doing the heavy lifting on their own development machines. They're using tools like Keras, TensorFlow, Pandas, Scikit-learn, PyTorch, NumPy, et cetera, to actually explore data, to refine and cleanse data, to fine-tune their models, et cetera. Now, when they're running their experiments, what I typically tend to do is, because if I can run basic models, and I'll show you a demo of this in a few minutes, but when I run models, they tend to take a long time, even on my MacBook Pro, so I will use tools like Colab or Azure ML or Amazon Machine Learning in order to actually run through the training process even very early on as I'm working on things. So let me show you a quick example of what this actually looks like. So I want to start with what I am... Uh-oh, I'm spoiling our demo. You didn't see that. It's fine. See it. So what I started with when I started working on this talk last year is I wanted to work on an emotion detection model effectively. So I went to Kaggle. Kaggle is a very common place where you can find data sets that can help you sort of start by solving your problem. One of the big challenges of machine learning is, where do I get all the data that I need in order to solve a problem? There are a lot of really good pre-existing models out there, but Kaggle tends to be a great place to find other sources of starter data or starter models that you can work with. And this is also one of the ways that Kaggle does this is that they run competitions. And so they did a competition back in 2013 where you wanted to create effectively a model for facial recognition, facial expression recognition, right? And so there are, I think, 28,709 48 by 48 grayscale pixel images of faces that represent one of seven emotions: angry, disgusted, fear, happy, sad, surprise, or neutral. And so those 30,000 images have been tagged appropriately and can be used with data that it hasn't seen to, if you construct the model appropriately, in order to detect emotions yourself. So what I did is I downloaded this very, very, very large CSV file. I think it's a 200 gig CSV file that has all of every single one of those 28,000 48 by 48 grayscale images. And then what I did through the next part of the process was effectively just go through transformation, loading this data, making sure I get every single pixel, turning it into a Panda data frame, process every individual pixel to convert it from a 1 to 0 based for 255, and then go through the process of, and actually let me go ahead and kick this off so you can see it. We're not sitting around and waiting. Python 3, train. I will output the length of my train and test data. So I'm splitting 80/20 into train and test data so that I can run through the model through training and then just sort of validate a little bit based on the data that I have left over. And then I go through a data generator. If you haven't seen this before, a data generator gives you the ability to tweak the data a little bit so that your data set can be artificially expanded. So you zoom in by 10% or sort of turn a few of the images by 10 to 20 pixels. So when the model goes through the training process, it thinks it's actually seeing a new image, even though you haven't had to expand the data set. So the data generator is a very useful, this gets used a lot in TensorFlow and Keras to help you expand the size of your data set so that you can get a little bit better stuff. And then I actually go through building the model. And this in Keras especially is my sort of declarative way of specifying I'm building a convolutional neural network, and I'm building one layer to the next. I have a lot of hidden layers inside of here. I think there's 8. So I'm sort of working, if you remember the diagram from earlier of the different connections between layers, I'm basically going through and creating an 8-layer model that Keras uses to determine, okay, how do I go from these images to detecting an emotion on the other side? And what it will do as it goes through the process, it'll start to figure out, okay, if I see a upturned pixels that represent a person smiling, there's an indication of happiness. Or I see the other way around, indication of sadness. Or if I see the brow furrowed a certain way, I can sense that there may be anger there, something along those lines. And it sort of extracts it over time at just looking at individual pixels and also where pixels occur in relation to one another. So when I actually run this, what you end up seeing is just a quick output. Okay, this is an output of what the pixels actually look like. So this is what the CSV file effectively looks like. Every single pixel was 0 to 255. And then the motion coded to the emotions that I shared earlier. And then we get into the actual layer. So you'll see I go through an input, convolutional 2D, activation over and over and over again as I go from one layer to the next. And then during the training process, I start doing this. And so what I'm actually doing for training, when I do fit, I'm running through the model 110 times. And you notice I'm running this on my two-year-old MacBook Pro. This is going to take hours if I actually run this on my machine. So I'm actually not going to continue it. But that is sort of what the training process looks like, especially if you're starting purely with Python, of creating something from an existing data set. But ultimately, there's a lot here, right? This is a lot of manual creating of a model, of sort of trial and error. There is a ton of work in this process in the early parts of a machine learning project. One of the things that I want to mention here is that there is a train, predict, and tune loop. So when I went through and built this model last year, what I just showed you, that 150 or so lines of code, was several weeks worth of fine tuning. It was several weeks worth of the data collection piece. Usually a very hard piece. For me was easy because I was able to pull that from Kaggle and just move forward. But you go through this process of collecting, preparing, another very, very time-consuming piece of the process, training, testing, evaluating, tuning and refining, exploring. Then you get into deploying, and then the challenge of maintaining, updating, and refining as data comes along in the future. Once you get through that deployment part, once you get through the training part, you get to do the fun part. The whole reason that we do machine learning in the first place is so that we can take data that we haven't seen before. So in a typical training process, the network is learning by tuning weights to reduce error. Remember I said before, the whole point is you're creating a model that allows the machine to find a correlation between the inputs and the outputs that you want to see, so that when it sees data that it hasn't, when it is presented with data that it hasn't seen before, those weights are applied against that data so that it can make a prediction. This is the fun part. And usually when you're doing prediction, you're still using libraries like TensorFlow, Keras, or OpenCV in the case of image recognition. So let me actually show you that piece now. So assuming that we've all been sitting here for hours, aren't you glad I'm not going to make you actually watch this all finish? We can actually go through the part of predicting now. So ultimately, what I get out of the training process is this model. This model represents, I actually ran the number of epochs that I ran. So I was running 110 before. 130, I think I ran about 150 times in order to get to the right place here. And then I got about a 66% accuracy. So even after that long and with a relatively large size data set, this model is only about 66% accurate, which for the purposes of our demo is fine. I'm not going to run it in production, but that's the model. And then I have an image that I'm providing to that, and I'm basically using OpenCV to load up the image so that I can put a bounding box around it. I load the model, which pulls in the HD5 file from before, and then the real important piece here is I am performing in my classifier a predict. And so this is still TensorFlow. What I'm doing with TensorFlow is I'm providing my image, and then what it's doing is instead of running through over and over again, it's taking those weights and it's running it all the way through the model one time. All the way from my input through all the hidden layers into the output, and then ultimately giving me an emotion that comes out the other side. And so when I now run this, no such file or directory. Oh wait, that's the wrong one, that's why. There we go. So when I run this, it's opening up TensorFlow, and now notice that I'm getting an array that represents all the different values and then the result in each of those. And I'll show you the image, but keep note here that the execution time is about 2 seconds. So even running prediction on my local computer took about 2 seconds for it to run completely through that entire process. So now I'm going to open up this was the image that I took earlier. Very silly image of myself I took about 30 minutes ago, and the prediction that came out the other side. Thinks I'm happy. That's pretty good. Frankly, the reality is that these data sets, and one thing you'll see a lot when you're working with data sets, is that they're not always evenly distributed across all of those emotions, right? If you look at the source data set, there's a whole lot of happy images in there, so it tends to, happy is an easier way to get the right prediction. There's not a ton of neutral images out there. This data set tends to use neutral when it just doesn't know, when it can't figure out what's actually happening in the image itself. It's the I don't know result. But that's the prediction piece. And that took about 2 seconds for us to go through. So once you're happy with that, once you have something that you think you're getting good results on, the model tends to work even with data it hasn't seen before, it's time for deployment. TensorFlow and Google Cloud, they have an option called TensorFlow Serving. You can use Amazon Machine Learning and Lambda, Azure ML and Azure Functions. This tends to be an important piece of the step, because you'll notice that for me to actually run that locally on my machine was about 2 seconds. I'm running on a CPU. All of these cloud providers have either GPUs or their own FPGAs that run prediction, or in the case of TensorFlow, their TPU or tensor processing units. This is all hardware that was custom built for the purposes of doing vector and matrix multiplication, which is effectively all that machine learning is, just performing a lot of math over and over again. However, there are also, with these cloud providers, a lot of canned models already. So a lot of what I just showed you in terms of finding a model, building your own sort of thing for emotion detection is already available in other cloud providers. So if you have a vision detection problem or speech language knowledge search, there are a lot of pre-trained APIs out there that you can use. Now, this is an example of what Azure has available. Microsoft has a lot of different APIs available under the Cognitive Services banner. The one drawback of using these is you're not going to be able to find out how these were trained, the data sets they were trained on. Microsoft does not give you the source data set. This is sort of, they consider these models as a part of their intellectual property. So I've tried to ask questions about how accurate these are, source, data, all this kind of stuff. They haven't at least given me the information, so it's really hard to know. You're relying on a black box largely, which is something that I know is a bit of a problem in the AI space, but you do at least get these things for free as opposed to having to build that from scratch. So emotion recognition is actually one of the pieces of the puzzle here. So we can do that using the Azure Face API, the oddly and funnily named Azure Face API. So I have another example of this as well. And I'm still using Python here, but effectively all I'm doing is creating a CLI tool that uses an API key and URL that I have set up in my own Azure account. And no, I'm not going to show you. You can't use my Azure account. And then pulls out the, uses the Cognitive Face Python package and performs cf.face.detect. Now, one of the things that's sort of interesting about the Face API is that you can actually pass in a comma delimited string of all the things that you want to see on the other side. So it's not just emotion detection, but you can ask the API to give you age, gender, head pose, smile, facial hair motion, all this kind of stuff that's available in there, which is really interesting. And it also gives you a bounding box that you can use to draw around where it actually detects an individual face. And this API works by default with multiple faces. You can send it an image of 5 and it will actually give you a two-dimensional array with all of the results that actually come out of that. So what I'm doing here is I'm going to draw the bounding box onto the screen and then provide the predominant, sort my list of emotions, and then return the top emotion. And then I'm going to draw that. I'm going to draw both the bounding box and the emotion onto the image using the image draw package. And then I'm going to show that to you. And also log the execution time. Remember, we were at about 2 seconds for 2.12 seconds here before, when I was running completely locally. So now if I run my cloud-based detector, so I'm going to use a different image that I also took this morning, and there we go. So that actually saw happiness as well, and notice that my time here was about 4 seconds. So a little bit longer, but I think that's just conference Wi-Fi latency. What you do get out of this, however, you do have that, you're at the mercy of latency on those networks, right? When I run these at home, maybe it's 1.5 seconds, maybe it's 2 seconds, what have you. You definitely get a close-ish performance in terms of running on the local machine versus running the cloud, right? I get all the speed of Azure's infinite cloud computing capability. The drawback is I have to rely on latency, which a lot of times can be out of my control. So one of the things that I haven't spent too much time talking about yet, but I want to talk about now is that, when we're going through the process, this iterative loop here, this is all local development here. When we're going through preparing, collecting, defining the task, when we're working through testing and validation, we're working with training and validation data. A lot of these other pieces here is cloud-based, right? When you're going through testing and evaluation, if you want to increase the speed of this feedback loop, you're largely going to run your predictions. You're going to run your tuning and retraining loops on beefier hardware than your own machine. And so this work all tends to happen very much in the cloud. The challenge here, and I've hinted about this already, is where does our real-time inferencing data come from? Where are we actually getting all of the oodles and oodles of data that we're actually using, even if it's a vision model? Where are our images coming from? If we're doing sensor network work where we're preventative maintenance or something along those lines, where is that data actually coming from? And this is what I want to spend the rest of the time today talking about, this idea that Really, the real future work of machine learning is in the IoT, and it's not just in the data collection phase, but also in our ability to increasingly perform the kind of inferencing that I just showed you in local networks and on microcontrollers on cheaper hardware so that we can get the lower latency while at the same time getting privacy in our systems. So, let's talk a little bit about the IoT in general and this idea of how the IoT functions with this concept of the edge and also traditional devices. So our traditional distribution between the Internet of Things and the cloud was this idea of the cloud was sort of your wonderful place where you had infinite computing, lots and lots of power, anything that you could possibly do here, you could do here. And on the Internet of Things side, we had these relatively low-powered microcontrollers, but we could put a lot of them out there, right? And in the last 7 years, what we have seen is this has been borne out. The kinds of devices that you used to deploy in IoT systems cost $40, $50, $60 per device years ago, now are sub 10. In the case of a system like the ESP32, $2, $3 devices at scale, where you can actually populate your sensor networks with oodles and oodles of devices without having to really do much in terms of trading off power. But there is definitely this dichotomy between the two. You had lots of power in the cloud and lots of devices. And then a couple of years ago, I don't know who's to blame here. Maybe it's Gartner. Let's blame Gartner. They're easy to blame. We came up with this term, the edge, right? We started talking about this concept. There's this sort of weird DMZ between the cloud and the IoT that represented some other thing. I don't know what this term means outside of everyone's favorite Irish lead guitarist. I don't know what the edge really means. But we have used this term to distinguish sort of this middle ground where you had computing that was a little bit more powerful, but not in the cloud, right? It was a bit of both. It was more powerful, but kind of more on the expense scale, closer to individual devices. So one of the first things that I want to dispense with today is this idea of the edge being something different. It's not a third thing. The edge fundamentally is the Internet of Things. And in many, you'll hear from a lot of people, if you are a Microsoft developer or you're in the Microsoft ecosystem, Satya Nadella actually never uses the term IoT, at least not for anything that I've seen. He uses the term edge to describe sort of everything that happens outside of the data center. I'm fine with that. The reality is, if we're going to call it, whatever we're going to call it, it's really just one thing. I do prefer the term the Internet of Things because it still rolls off the tongue, IoT. But the reality is that this is one thing, right? What we're doing outside of the cloud, whether it's with single board computers like Raspberry Pis, or our own hardware, or even servers that we have deployed in an edge environment that we buy from a provider like Microsoft, it's still happening inside of your own local environment, inside of the IoT. And the reality is that the IoT is the source of that data. Now, I'm being overly simplistic when I talk about low-cost sensors, temperature, humidity sensors, things like that, but the IoT is the source of your real-time inferencing data. If you're doing a predictive analytics project or predictive maintenance project, the sensors that are detecting vibration, that are detecting movement, that are detecting heat, humidity, things like that, those are coming from your IoT networks, from your IoT devices. So those are the sources of real-time data, but they're also the source of all this, the training and validation data, right? I think one of the biggest problems that we have in the IoT space right now, at least as it comes to machine learning, is there's not a Kaggle data set for like vibration detection of an engine, right? There isn't one of those, at least as far as I've seen. A lot of the problems that we're solving in machine learning in the IoT space are relatively net new problems, where if you're an elevator company that's trying to make sure that your systems are relatively stable, that everything continues to operate, you're probably the first company that's thinking about that, and your competitors have not published their findings for you to use and benefit from, right? Largely, we are solving these problems ourselves internally, and so our IoT networks are the source of that data. So what I think is really fascinating here is that we are getting to a place where not only can we use the IoT as our source for the data that we're training models from, but there's a world emerging where we can actually do inferencing. We can actually do the prediction part of that process, not on a cloud, but on microcontrollers and on single board computers that are in our edge data centers or in our ecosystems. And the reason for this, I think the three reasons why I think this is really important are volume, speed, and privacy. We'll talk about each of those in turn. One of the big reasons why volume is important here is because the reality is that with IoT devices, we're not talking about millions, but billions upon billions, and one day probably trillions of low-cost sensors that are detecting everything from temperature, humidity, to heat, to ambient values, to vibration, to light levels, you name it, right? There are tens of thousands of different sensor types out there you can get on the market, some that are pennies on the dollar. We are connecting everything to them, and we are connecting every single device to each other. And we've gotten to the point now where our IoT devices have actually outstripped the number of mobile devices out there, the number of physical computers out there. So we're working with a computing infrastructure that is far larger than anything that we've ever seen in the mobile world and that we've ever seen in the desktop world as well. And the problem that this creates is that the more and more devices that we bring online and the more and more data that we collect in those devices gives us a larger and larger need to be able to use that data for something on the other end, right? We're not connecting all of these things and sensing from all these things for nothing, right? We're gathering temperature data and humidity data because we want to do something with it. The more and more data that we collect gives us a larger and larger need to actually store that data somewhere, but that does create a bit of a problem. The problem for that is that the cloud itself may be infinite, but our pipes to the cloud are not. Right, so we can collect larger, and we can get cheaper and cheaper IoT devices out there, and we can get larger and larger instances in the cloud. The problem, we are still limited by the fixed infrastructure of our ability to take data and actually stream it into a cloud environment. And this is really important in the IoT case, because if you're doing something like vibration detection, that's a very common use case for IoT. If you're doing vibration detection on an industrial dishwasher, for instance, you're collecting X, Y, and Z values from an accelerometer over and over and over again, hundreds and hundreds of times per second, likely 1,000 times per second, right? Every single millisecond you are looking at what are those values, how does it change? And you need to make a decision based on the value. So if you're collecting 3 values 1,000 times a second over the course of an entire day, where are you sending all that data? What are you doing with it? And so we now multiply that times 1,000 different devices. You're on 20 different sites, et cetera. You can see this becomes a scale problem really quickly. And the problem is that we can't just cut that down, right? We can't say, well, the solution here is that we just need to collect sensor data less. Because the reality is that in the machine learning context, we always need more data, right? The biggest problem that we have in machine learning is there never seems to be enough. Well, in the IoT world, there is data aplenty, and that's actually never going to be an issue. The issue is always going to be what we do with that data, how we collect it, and then where we send it to actually make a decision. So if we're doing inference, right, we're collecting all this information, we're sending it off to the cloud, we're actually relying on the cloud to then ingest all that data and make a decision for us. But the reality is that all of the things that we're sending along, temperature, acceleration, et cetera, that's not the thing that we want. The thing we want is the prediction. The prediction is the whole reason we're collecting that data in the first place. The ability to make a decision, to detect an anomaly, to find an error before it happens is the reason why we're doing all this. All that raw data actually doesn't matter to us in the context of the cloud. It's not anything that we need to store. And so if you look at this in the preventative maintenance context, as I mentioned already, what does this look like, right? If we are actually collecting X, Y, and Z values, and then we're actually streaming that data over and over again, we're relying on the cloud to actually do something for us, that can be really useful, right? We can get something relatively fast, it can detect an anomaly. But if our cloud infrastructure goes offline, what do we do then, right? This is actually one of the biggest weaknesses of machine learning in the IoT space right now, because we're relying on the cloud. If we actually lose our connection to the cloud, we lose our ability to do anything useful. We can't predict anything. We can't log anything, right? But so there's really effectively no cloud when you're offline. And this does happen, right? Even in rugged industrial settings, just because you have something wired in Ethernet doesn't mean that your backhaul, that your backbone is not going to go offline. It happens far more often than we like to admit. But if you're actually doing this inferencing locally, if you have a single board computer, or you have a microcontroller that can do this for you, you actually don't have to rely on the cloud. You don't have to rely on that connection being online. You also don't have to worry about the latency that that creates. You can get to the same result without having to rely on the cloud in order to do that. And then finally, and probably my favorite reason for doing inferencing inside of the edge or inside of the IoT is the built-in privacy that you get with this. So let me go back to my vision detection example, right? I showed you a couple examples earlier. This was a different image I took months ago where I'm taking an image of myself, sending that up to the Azure Face API, and it's giving me a result. It interpreted that as anger for some reason. So I wasn't angry, I was really quite happy. But I'm actually sending this image. Now Azure may not actually keep this image, but that doesn't matter, right? Because that raw image with personally identifiable information, info about myself, you could zoom in on the bookshelf and see, oh, what is Brandon reading these days, right? Or you could infer some context about me based on what you can see in the background, et cetera. That image gets streamed across the internet. If you've hacked the pipe, you can get the image, right? This is our large problem in the IoT today, is that our personalities, the things that make us unique, are things that are being streamed and shared into the cloud. We're not happy about that. So if you do vision detection at the edge, what you get instead is the thing that you want. The whole reason that I sent that image to the cloud is because I wanted the Azure Face API to tell me what it felt like my emotion was at that moment. But if I'm able to do this locally, then I get the thing that I want, right? I can get the emotion that says, okay, this is 66% anger and 33% disgust. That's probably a little bit more accurate. So this is the thing that I want, the actual prediction based on the API. And if I'm doing that locally, now I can send this to the cloud, right? The output of the inferencing result is what I want, and that's the thing I can send. And this is infinitely more private because there's nothing that's personally identifiable about this. This is the thing that I actually wanted. And if the cloud doesn't have to take the private data in order to get me that result, then I'm better off for it. So there's a couple of different ways that you can do this today. So you may ask yourself, okay, well that's great. I would really love to do inferencing in my own ecosystem, but I'm not going to go and buy one of Google's expensive TPUs in order to put in my own edge environment. And I can't wait 10 seconds to find out if a vibration sensing or if a XYZ value I got from my accelerometer is indicative of a failure of an engine. There is actually there's a couple of vendors that are creating custom hardware in the single board computer form factor that allow you to do this. Google has a couple. One is the Google Coral, which is about $150 dev board, but they have a module inside of here that can be purchased for cheaper at scale. And this is effectively a TensorFlow processing unit. So this is a coprocessor that they've put on a board that looks a lot like a Raspberry Pi and has a Raspberry Pi compatible pin header that is designed to do that complex matrix and vector multiplication very quickly. So you can run your programs on it, you can offload the inferencing piece to their TPU and get the results out very, very quickly. They also sell a USB accelerator that you can use with an existing Raspberry Pi 4. Raspberry Pi 4 has you can use it with a Pi 3 too, but the reason why I mention a Pi 4 here is because the Pi 4 has USB-C, which is much faster than USB 2. And if you use the Pi and the USB accelerator together, and the USB accelerator is like $79, you can actually get relatively close inferencing to what you can get in the Google Coral. And let me dig in on this just a little bit because I love geeking out about these things. This TPU module that's on here is a quad-core ARM Cortex-53, but it also has an ARM Cortex-M4, so it effectively has a CPU that runs the main operating system. It is a Linux single board computer. There's a custom Debian distribution that Google provides on there called Mendel. And then it has a coprocessor that does all of the ML inferencing stuff. It has Bluetooth, an 8 gig MMC, several USB connections, audio and video, micro SD, all the good stuff. And like I mentioned already, the 40-pin GPIO expansion header that is pin compatible with the Raspberry Pi. But I actually want to show you what this looks like because it's pretty cool. This is the board. I have it right here. You're welcome to come and check it out after. Very similar in size to the Raspberry Pi. I think it's just a tad bit larger. But I actually have this connected to a webcam. And it is running a server demo that is doing face tracking. So I'm running TensorFlow Light. So the Coral, of course, it runs TensorFlow because that's Google's framework, largely supported and sponsored by Google. But what it's doing is it is doing face detection and then drawing a bounding box that also includes the confidence that it's actually seen a face. But you'll notice here as I'm moving around that this is actually inferencing really, really quickly. I'm getting about 130, 120 frames per second on this as it's running, only on this machine. This machine itself is not connected to the internet. And it's running about every 10 to 20 milliseconds, very, very quickly. Now, compare that to 2 seconds to do inferencing before with a motion detection, 4 seconds if I relied on the Azure Face API. And the beauty of this, and I promise this is not being recorded, so I'm going to show some of y'all's faces. Hopefully, you're okay with that. But this is actually, hopefully can pick up multiple, too far away. See if I'm too far, let's see if I can do this. Anything? Okay, I see one, 16%. You're 16% of face. Hope that's okay. All right, I was working a little bit. All right, so that's what I get for doing unplanned demos. But it can actually do multiple object detection as well, and it does not degrade the latency on the individual devices. So that's actually really interesting. So for $150-ish, $140 if you go with the Pi plus the Coral USB stick, is that you can actually do inferencing now a whole lot faster, right? You're getting low latency, you are getting a result without actually streaming that image across. So in the context of a production environment, if I wanted to make sure that I was detecting a person when they walked past a security camera, I can send my alert to the cloud, but I never send the actual raw image, right? I'm not sending frames to the cloud and asking for a result. I'm just sending, hey, there was a person detected. You'll never know who it was because I'm not sending who, I'm not sending the PII, I'm sending just the fact that we found someone, and here was the level of confidence. So, now we talked about this in the context of single board computers, but where does this leave the Internet of Things in general, especially our microcontrollers, these low cost, low power devices that are actually sensing and doing a lot of the heavy lifting in our environments. And really there's two pieces where I think the MCUs, microcontrollers themselves, will become very important as we get deeper into this machine learning world. One is in the collection and coordination, and second is actually inferencing on these low cost devices. So some cutting edge stuff that I'll share here over the next couple of minutes. So one of the things that's really important here is I want to continue to underscore is that the IoT will continue to have a role in building out the ML solutions of the future, right? Our machine learning devices are the ones that our IoT devices sense and share, right? They're the ones that are collecting the data that we need. They're the things that are actually responding to networks as well, right? So when we actually are doing inferencing at the edge or in the cloud, it's our IoT systems that are actually taking action. They're actually doing something based on inferencing, based on the things that we're actually seeing. So the opportunity that something like this edge, this Google Coral, is not as a replacement for our IoT networks. One of the things that I have observed in the past that people tend to do with products like the Raspberry Pi is that they sort of treat this not only as their, it would be very easy to make the mistake to be like, all right, I've got the single board computer here, so it's now going to be my network device, plus it's going to be doing inferencing, right? What I would recommend doing in this sort of environment is to add the Coral, add the Raspberry Pi into your system, but not ask it to really do anything other than be the inferencing workhorse, right? This is effectively like a very small little server in your data center or in your infrastructure that allows you to do nothing more, not to have to pipe data to the cloud, not even to necessarily be connected to the internet, because that gives you something that's more private, more secure, but to allow your IoT infrastructure, your IoT network to do the sensing and sharing and to interface with those environments to stream data across for outcomes, for it to actually perform the prediction. The other thing that's really interesting here as I close in the last couple of minutes is that we're actually getting to the place now where as cool and exciting as this is, the reality is that you're still at $150, $100 price point in order to do this level of inferencing outside of a cloud, outside of a data center. But there is actually a lot of work happening. Two things I think that are going to be really fascinating that are going to allow us to do more real-time prediction actually on lower cost, sub $20 devices. The first is on microcontrollers. If you are at all a TensorFlow fan, I would highly recommend checking out this book, Tiny ML, from Pete Warden and Daniel Sintiake. They actually, both on the Google TensorFlow team and have done a lot of work over the last couple of years, along with the Google TensorFlow team, to actually support Tensorflow Light on low-power microcontrollers. So Arduino Unos, particle argon photon devices, particle photons. You can use this with Adafruit devices as well, where you can actually run ML inferencing on these low-cost, low-power devices. And the way that this works is that you go through the traditional process of building and training the model. So for instance, let's say I want to actually build a model that does the canonical straight line equation, y equals mx plus b. So I know my x values, I know my y values, and I'm going to build just a very simple linear regression model, sequential model that then tells me, okay, what are my x, what are my m and b values that give me the y that I need out on the other end. So I do the exact same thing that I do when I'm building a TensorFlow model for running in the cloud, but when I'm done with this, I convert my model to TensorFlow Light. The difference between TensorFlow and TensorFlow Light is really out of scope for what we're talking about here, but the important thing to note is that TensorFlow Light gives you much smaller models. TF Lite was originally created for running on mobile devices. TensorFlow Light Micro now with microcontroller support has now been tuned to create even smaller models. And once you've got that TensorFlow Light model, you want to create a C array that represents the model. And so one of the challenges on microcontrollers historically is that not every MCU has file systems, right? A lot of Arduino style devices don't have file systems. You can save a model and then load it up in memory. And so a lot of times what you'll do in this case is you'll create a very easy just C representation. And this actually works because machine learning models are really nothing more than numbers. So they're very, very large files of numbers, effectively matrices and vectors. And so you load up the model, you create a C array that can then be loaded in memory by your program. And so when you're using then TensorFlow Light on an embedded device, the way that this works is you load your C array, you pull it in as a C++ file, you then capture real-time data. In the context of this demo, I'm just getting a random number between 0 and 1, setting that into my input tensor. You run inferencing. So basically this is just interpreter.invoke on a microcontroller that's running C, and then you process the results, right? In this case, I can see my X and Y values stream across the serial console, and then you can do an IoT funny thing like show that line on a connected screen, right? This is a very contrived example, but I wanted to show you the process of model creation is the same, and there's just a little bit of work that you need to do on the microcontroller side in order to actually make this work. But I'm going to show you something a little bit less contrived here as we close, and actually show you a demo that I have built with this device. So I have a particle device that's actually connected to a 9 degrees of freedom accelerometer here. And what this is doing is this is actually going to allow me to do gesture detection effectively. So I have 3 different models. I have 3 different gestures that I have trained. I will use the device to detect when I have actually drawn a ring. This is my magic wand, where I've made a wing gesture in the air, or when I've done a slope, right? And so this has been trained on a few dozen different individuals to actually detect the X, Y, and Z changes based on those, and then can actually run that inferencing in real time on my device. And so what this looks like, and this is all C++ code here, what I'm doing is loading up my model as I showed you in the example before, and here's what let me actually show you a bit of what the actual model looks like. If I can pull this open, the model data. That's the header file. This is effectively what my magic wand model looks like. I'm not going to scroll all the way to the bottom. It's just a bunch of numbers. I think it's about 18K. So the beauty of TensorFlow Light is we've gotten in this environment where, and microcontrollers have more memory than they did 2 and 3 years ago, where you can load 18, 20, 30 kilobyte models into memory and be able to run those pretty quickly. And so what I'm doing is I'm loading up my model, registering the operation. So I'm doing a convolution. This is a convolutional neural network that ultimately gets me out a softmax, which is a prediction between 0 and 1 of all of my individual gestures. So it gives me an array similar to the emotion model, which gives you an array of the different gestures and then their values. What this is going to give me is an array that represents the value between 0 and 1 and the likelihood of each of the gestures actually being performed. So I'm loading my inputs, and then I'm reading accelerometer data. And this is actually where the IoT part comes in, right? Where you're actually, where's my accelerometer handler? In the case of in an IoT system, this is really where the hard work comes, is where you're actually trying to collect data in real time. And so I'm using my IMU library from the Adafruit device, getting my X, Y, and Z values, and then basically just getting a sample over the course of about a second of all of the different changes. And because this is a convolutional neural network, it can determine if my X, Y, and Z values were here, and then we're here and here, that's probably a slope, so that's the prediction I'm gonna make. If my X, Y, and Z values sort of move in this direction, then that's the prediction I'm gonna make there. So you're capturing that data every millisecond, but then grouping it together and then effectively sending it into the model. So with the data that I get, and what the read accelerometer does is it actually takes that value and then saves it into an array and then sends it on to the, sends it back to me so that I can make a prediction. So now what I'm doing when I invoke is I'm getting my output, which is that array of the 3 different values, and I'm handling that here in the output handler. And so what I'm going to do here is I'm going to turn on the RGB LED on this device based on what the prediction is, but I'm also going to output this to the serial console so you can see the different gestures that I made. So let me run this really quick. I'll turn on my serial monitor, and I'm going to perform some predictions. I'm not going to do the predictions. I'm going to make some gestures and see if this thing actually works. First start with a wing gesture, down. Got that pretty quick. We'll do a, no. It's false positive sometimes, still early days in machine learning. I'm gonna do a ring, see if we can get that one to show up again, and then a slope. And that'll make that. So this is really important. This prediction was happening very, very quickly. Nothing was being sent to the cloud. All of the actual inferencing and real-time work is happening on what is a $12 device, right? The microcontroller that's on here can be bought at scale for 50 cents, right? These are the kinds of things that we are seeing in this world where we can actually stop relying so much on sending everything into the cloud, but embrace some of the power on these increasingly powerful devices. The other thing that's interesting here is federated learning. So federated learning is a very new concept, and it's new now to mobile devices, but it's this idea of being able to distribute inferencing across a network of devices. So this is very similar to what led us into cloud computing today, right? The genesis of cloud computing was that Amazon had a whole lot of infrastructure sitting around that was idle, and they're like, hey, why don't we just rent this out to other people? Federated learning takes that same concept, and I think this is where we'll see a lot of power in the IoT in the next couple of years, where we have a lot of IoT devices and sensor networks that are just idle a lot of the time. They're sitting, they're sensing, they're sending, and they're going back to sleep. Right? So federating learning basically allows us to take this idea of distributing our algorithms, because again, a machine learning model is just numbers, right? And you can take an array of numbers and have it live in different areas. And you can have your cloud perform the first couple of levels of prediction and then send it to the edge and then do the last part on the IoT and actually get that power of using these networks of devices together to get the result that we want. This actually allows us to blend the idea of privacy and scale pretty well, right? Because if you do your first few layers of prediction in the sensor network, you're obfuscating your input data enough to make it more private, to sort of remove the PII, before you send it along down the line if you need that speed, if you need that extra power. So I mentioned when I started today, I really wanted to communicate 3 big things. One was that machine learning is human teaching. Second, that training is meant for the cloud. And then finally, the real work of machine learning is in the IoT. So as I leave you today, I want to share just a couple of different recommendations. If this is interesting at all to you and you want more information, feel free to come and chat with me afterwards. But I would encourage you to explore machine learning inferencing with single board computers. If you already have a Raspberry Pi, grab the Coral USB compute stick. There's other devices out there. NVIDIA has a device called the Jetson Nano that you can also purchase that allows you to do the same style of GPU-based inferencing. Or grab the Google Coral. This is a really exciting time. There's some great demos out there. And then also, explore Tensorflow Light for machine learning on MCU. So if you work with TensorFlow today, there's an entire section on TensorFlow Light for microcontrollers. You can check out Pete and Daniel's book as well. This is really fascinating. I think really the future of where the cutting edge of ML and especially, I think the work that's going to get us out of the trough of disillusionment, sort of back into the plateau of productivity using Gartner terminology, into machine learning is going to be a lot of the work that's happening here in our edge devices, in our IoT environments. So thank you very much for your time today. I have a few minutes for questions, but I'm also hang out afterwards. So thank you. Yeah.
In your Magic Wand demo, are you streaming individual accelerometer points to the network, the Tensorflow Light? Are you streaming individual stuff to that, and all the state is living in that, or are you buffering up a big, the last 2 seconds accelerometer data every time and throwing that at the?
Yeah, that's a great question. So I can dig into the details a little bit, but in reality what's happening is I'm capturing data in real time and then sort of skipping every in order to give me a little bit of a smaller payload. So I think I'm skipping every like 10 readings. So instead of getting 1,000 when I do this, maybe I'm getting like 200 right here. So I'm skipping a bit to get a more tuned array and then sending that in. And that's ultimately what's doing the prediction. And part of that is just based on the device and how quickly it tracks. But I could easily capture everything and send it, but it's all living locally within the device itself as it's streaming across. So.
And how much RAM is the model using? You said it's about 20K of ROM.
Yeah, the RAM usage is about similar. I think I don't know that I ever targeted it specifically, but I've never actually had issues running out of memory on these. Now, there are some models out there where you're going to need more, definitely. There are actually person detection models that run with a connected like Arduino webcam, and those can be like 200K, and those are a lot slower. So it's early days in a lot of those, but there's not taking up a lot of RAM at all. Yeah. Great. All right, so I'll be up here available afterwards as well. Thank you all.